Hey, Algebra 1. Today we're going to continue our discussion on mathematical functions, and we're going to look more specifically at identifying the domain and range of a function. This lesson corresponds with page 71 in your Springboard books. We're not going to go through all the problems. We'll go through a handful of them so that way we can keep this lesson short for you. Okay, let's go ahead and get started. So some important vocabulary words you're going to need to know for this are the domain and range. What are they? We covered them already in our previous lessons, but more specifically, the set of all inputs for a function known as the domain of the function. So anything we put into a function, that's going to be our domain. And then likewise, the set of all outputs for a function is known as the range. So we put a number in, get a number out. That output value is part of your range, okay? When we write a set of numbers, we're going to talk about this a little bit more in depth. They can be written using set notation, which are these curly brackets right here, okay? So if we're given a set of ordered pairs like this, the domain would be all my x values or the first values, so 1, 3, 5, and then the range would be 2, 4, 6 because those are all the second values, those y values, okay? So once again, when we write a set of numbers, we can write them kind of in order, like in a sequence. They not necessarily have to be in a sequence where they have an identifiable pattern, but they can be written just like we see right here. So if we have the domain 1, 2, 3, 4, 5, we can have their range written as 6, 8, 10, 12, and 14. Okay, so once again, that's one way we can write the domain and the range here. If we look at identifying domain and range in forms that we're familiar with, so for instance, for part A, it says the input and output in a table here. Remember, the input is all my domain values. So to make things a little bit nicer, let's go ahead and put them in order here. So for my domain, I would just have 3, 5, and 7, because it goes 7, 3, and 5, but let's put them in numerical order. And then the output, once again, we want them in ascending order for 6, -2, and 1. So I'll put it as -2, 1, and 6 like I have right here. Likewise, in the mapping right here, where the numbers start, where the arrows start, those are my input values, my domain values. So that would be 2, 6, and 8, which I have right here. And then 4 and, that's -3. I'm sorry, let me fix that really quick here. So -3 and 4 would be my range values. Now you're probably thinking, now is this a function? Is it not a function? Let's take a look here. Remember, in order for it to be a function, every value in the domain must be assigned to exactly one value in the range. And in this case, 2 goes to 4, 6 goes to 4, and 8 goes to -3. There's no overlap here. There's no number being assigned to more than one number in the range. Therefore, this is a function. So when we have less numbers in the range than we do in the domain, that is okay. All right. Looking at another example from formats that we're familiar with. If we have a graph, we want to identify our domain as all of the x values of our ordered pairs or of a point or a value on a graph. So my x values are going to be 2 because that's where the first point is, 3, and 5, like I have them in numerical order here. Same thing with the range. The range is all my y values. So that would be 1, go to the next point, which would be 3, and then 4. And then last but not least, if we have a set of ordered pairs, we can reorganize the ordered pairs so that way they are in domain and range numerical order. So in this case, I look at -7, +9, and -6, and I just rearrange them in numerical order. So -7, -6, and +9 are my domain. Same thing with the y values of these ordered pairs, 0, -3, and 2.5. I just rewrite them in numerical order, -3, 0, and then 2.5. Those are my range values. Now, you don't have to put them in numerical order. I just like doing it that way because I like to be thorough in how I do my math and how I do my notes. All right, a couple word problems I want to take a look at are right here. Consider a vending machine where inserting 25 cents dispenses 1 pencil, inserting 50 cents dispenses 2 pencils, so on and so forth, including all 10 pencils in the vending machine. Okay, so if there's only 10 pencils in there, that means we only can get 10 out. Okay, so in this case, my domain is what I put into the vending machine, which would be, I could put 25 cents, I could put 50 cents. Oops, let me make this a little bit bigger so that way we can fit all our numbers in here. 50 cents. I can put 75 cents. I can put $1 in, $1.25, $1.50, because that's 6 quarters. I could put 7 quarters, put in $1.75. I'm going to run out of room here. That's okay, though. You guys will be able to follow along, no problem, I'm sure. So $1.75, that's 7 quarters. $2 is 8 quarters. $2.25 is 9 quarters. And then $2.50 is where I run out of money. And if I keep putting money into that machine, I'm going to get nothing out of it. Okay. And in this case, that's all in cents. For my range, remember, that's what we get out of it. We get pencils. So I could get 1 pencil, 2 pencils, 3 pencils. Once I make my text box a little bit bigger. 3 pencils, 4 pencils, 5 pencils, 6 pencils, 7 pencils, 8 pencils, 9 pencils, or I can get 10 pencils. And that's it, because that's all that's left in the machine. Okay, so that we put money in, we get pencils out. That's how this machine works. Okay, so those would be all valid answers. I could put, if I wanted to, I could put decimal points in front of each one of these to show like dollars. But in this case, oops, it wouldn't be 0.10, it would be 1.0. So if you wanted to express the domain in terms of dollars, you could, or if you wanted to express it in cents, that works as well, whichever way you're more comfortable with. But the idea is that we put a certain amount of money in, we get a certain amount of pencils back. Okay. Looking at another word problem with domain and range here. Okay. I have another machine that exchanges quarters for dollar bills. Inserting $1 bill returns 4 quarters. You may insert up to 5 $1 bills at a time. Okay. So I could put in $1. I could put in $2. Once this decides to work, there we go. $2, $3. I could put in $4, or I could put in $5. Okay, and what comes back is I could either get 4 quarters, I could get 8 quarters, I could get 12 quarters, I could get 16 quarters, or I could get 20 quarters back. Okay, so the idea is however many dollar bills I put in, I get 4 times as many quarters back. That's just kind of how it works when we convert dollars into quarters. Okay, and unfortunately, this machine will only let me put up to $5 at a time. Now, a thing that might come up is, can we put in a fraction of a dollar? Which, I mean, that'd be 50 cents, but can we get 50 cents out of a machine? That would make no sense. So in this case, we're looking at just whole number dollars here. Okay, so functions, as you probably have already seen, are number machines. We put a number in, we get a different number out. Might be a different number, it could be just one number. But in this case, when we have, like we see right here, sometimes a machine diagram is used to represent functions, kind of like what we have right here. It kind of looks like an engine of sorts. In the function machine below, the inputs are labeled X and the outputs are labeled Y. The function is represented by the expression 2x plus 5, which means that whatever we put into it, we multiply it by 2, add 5 to it, and that gives us our number back. So what is the output if the input is 7, if the input is -2, or the input is 1/2? Well, we put in 7 here. We do 2 times 7, add 5 to it. Remember, our order of operations, got to do multiplication first. So 2 times 7 is 14. Add 5 to 14. That should give me 19, not 9. I apologize. If x is equal to -2, we should get 2 times -2 plus 5, which gives me -4 plus 5, which is just +1. And then 2 times 1/2 is 1. Add 5 to it gives me 6. Okay. Now, this is obviously just for this expression here. It's not always going to be like this. It may at some point, if you come across 2x plus 5 on a test or a quiz or homework or anything like that. But this is this set of domain and range is unique to this expression. Same thing if we try this. Think about it this way. Is there any limit to the number of input values that can be used with this expression? Meaning, can we use any number we want and get another number back? And that is, the answer to that is absolutely. Okay, there's no discrimination here in terms of what number we can put into a function. Okay, you'll learn about restrictions and discriminations of the domain when we get to Algebra 2. But for right now, we're not going to be looking at those. You can put any number in, you can get a unique number out. Okay, last machine I want to take a look at. What if we have something like this, which you probably did see in the Delta Math homework, which looks like this. We have x squared plus 2x plus 3 as my number engine or number machine here. Okay, we put a number in, we square it, add 2 times that value, and then add 3 to it to get my y. Okay, so for each one of these, it's kind of a general way of looking at this is if I replace a number in an expression, I want to make sure I'm putting that number in parentheses, okay? Especially if we have negatives and everything like that. So you want to have negative 5 squared plus 2 times negative 5 plus 3 for the first expression. Simplify this. Remember, exponents first, then multiplication, division, and then addition and subtraction. That's going to give me 25 plus negative 10 plus 3, and I can just go ahead and add everything down as from left to right here. So 25 plus negative 10 is 15. Add 3 to it gives me 18. So I put negative 5 in, I get 18 out. With 3/5, I wrote it as I wrote this fraction as a decimal, so 0.6 squared plus 2 times 0.6 plus 3. 0.6 squared is 0.36 plus 0.12, or it should be 1.2. I apologize, I'll have to redo my math. And then plus 3, that should actually give me 4.56. Not 3.48, 4.56 for that. And then last but not least, for negative 10. Negative 10 squared plus 2 times negative 10 plus 3. Negative 10 squared, negative 10 times negative 10 is positive 100. And then 2 times negative 10 is negative 20 plus 3. Combine the first two, I get 80. And then plus 3 gives me 83. Okay. All right, your exit slip will be found on our classroom page for this lesson. Make sure after you're watching this video, you click on the exit slip and do that. It's only 5 questions. And then your homework is lesson 5.2 practice on page 75 in your Springboard books. I will be posting that as soon as the class is done for today, so you can get started on it as soon as you are done watching this video. Hope you guys have a great day. We'll see you next time.